Philippine Mathematical Olympiad 2022 National Stage Written Phase, problem number 224th, day 1. Okay, so before considering this problem, if you wanted the next videos, subscribe my YouTube channel, turn on the bell, like the video, and if you wanted solutions or more explanations, send message through my WhatsApp number. It's here. Now let's consider problem number 2. Okay, it says the PMO magician has a special party game. There are entries labeled 1 to n. There are n sheets of papers labeled 1 to n. On each chair she attaches exactly one sheet whose number does not match the number on the chair. She then asks n party guests to sit on the chair so that each chair has exactly one occupant. And whenever she claps her hand, each guest looks at the number on the sheet attached to their current chair and moves to the chair labeled with that number. Show that if 1 is strictly less than m, less than or equal n, where m is not a prime power. When m is not a prime power and greater than 1 means that it has at least 2 prime factors. And it's really useful for the solution. It is always possible for the PMO magician to choose which sheet to attach to each chair so that everyone returns to their original seats after exactly n claps. Okay. Before solving this problem, we need to know permutation graph. It is also useful for SUMEC summer camp of Stanford and also many other exams and competitions. It means how to display a permutation with graph. We consider n vertices and then we can say we connect I to pi I. It means, for example, here direct with this direction I to pi I. So here 1 to pi 1, which 1 to 3, for example, for this one, 3 to pi 3, 3 to 1. 2 to pi 2, and it's 4, 4 to pi 2. For this one, 1 to pi 1, 3, then 3 to 4, 4 to 1, and 2 by 2, 2. Now, for this problem, because of this condition that says doesn't match the number on the chart, means, for example, we don't have this case that 2 is in place 2. If the number of chairs is here, the number attached must not equal. So here we can say that in the and we can prove that this graph always each out degree if you consider each vertex out degree and each degree is 1, so we can prove easily that this graph is union of these joint directed cycles. And also because we don't have something like this in the graph, it means that we don't have cycle with length 1. So the length of each cycle is at least 2. Now, let's see, we want to find what? We want to find some cycles, L1 to Ls, that sum of them equals n, because we have n chairs, so permutation is 1 to n. And we know L1, the elements here, after L1 to L1, they come again to the first case, to origin case, so multiple of L1. Now, if you want that all the, like here, this condition, if we want that all, it says everyone returns to their original seats after exactly m claps. If all of them want to reach, in the first case that they reach is LCM, because it must be multiple of L1, L2, Ls. So LCM of them must be m, and we know m is equal to P1 alpha, P2 alpha to Pk alpha greater than equal to, because m is greater than equal to. Now we should prove that there exists. The problem is that there exists. Why there exists L1 to Ls such that and Li are at least 1, at least 2, because we said that the length are at least 2, and some of them n, LCM of them m. Now we want to prove that there exists by using induction on K, the number of primes that m has. So the problem says m is not power of a prime, so k is at least 2. Now let's consider here I've meant k is at least 2 and alpha I is at least 1. So if we use induction on k, for k equals 2, you say n we know greater than m, greater than 1, and alpha 1, alpha 2, alpha and alpha 2 are greater than equal 1. If n equals m, it's so much easy. You can consider a cycle 1 to 2, 2 to 3, and n minus 1 to n, and class n to 1. Otherwise, if n is greater than m, strictly greater than m, so n is at least p1 alpha 1, p2 alpha 2 plus 1. Now we consider these p2 alpha 2 numbers, n minus 1 times p1 alpha 1, n minus p2 times p1 alpha 1, and n minus p2 alpha 2, p1 alpha 1. We want to say, and all of them are at least 1 because n is greater than equal this. We want to prove one of them is multiple of p2 alpha 2. How? We consider these numbers. We know there are p2 alpha 2 numbers. We want to say all the remainders when divided by p2 alpha 2 are different. So because the number of them is p2 alpha 2, so one of them is multiple of p2 alpha 2. Like what? When you have 5 numbers and all of them are different when divided by 5, so they have all the remainders. So one of them is multiple of 5. Here, instead of 5 mod p2 alpha 2, we say if 2 of them are congruent mod p2 alpha 2, we can cancel n and then multiply by -1. So ip1 alpha 1 is congruent to jp1 alpha 1. Because p1 and p2 are prime numbers and are different, so their GCD is 1. So you can divide both sides by p1 alpha 1, and it will be I is congruent to j mod p2 alpha 2. Since I and j are coefficient of them, I and j are between 1 and less than or equal p2 alpha 2. So when they are congruent mod p2 alpha 2, they are equal. Now we can say these p2 alpha 2 numbers mod p2 alpha 2 would be 0, 1 to p2 alpha 2 minus 1. So one of them is multiple of p2 alpha 2, 0. So n minus, for example, tp1 alpha 1 is lp2 alpha 2. And we know all of them are integer or positive integers here, we said. So n is tp1 alpha 1 plus l p2 alpha 2, which t and l are greater than equal 1. So here, because we said this and t and l are greater than equal 1, so you can consider tp1 alpha 1 and l p2 alpha 2, sum of them is 1. And because the GCD of them, p1, LCM of them, if I write LCM of these t plus l numbers, LCM of p1 alpha 1 to p1 alpha 1 t times, and p2 alpha 2 to p2 alpha 2, because we have L and T are greater than equal 1, so at least 1. We have T times greater than equal 1, L times greater than equal 1, so it would be p1 alpha 1, p2 alpha 2, which equals m. So for k2, we proved this problem. Now, suppose that for k minus 1, the problem is true. Now we want to prove for k. K is at least 3, because for k2, we proved that in the first case, base case. Now, suppose m equals this, if m equals n, so you easily again consider this cycle. So otherwise, we can consider that n is at least m plus 1. And m is p1 alpha 1 to pk alpha k plus 1. Now, suppose n, subtract p1 alpha 1 from n, it would be n equals p1 alpha 1 plus n minus p1 alpha 1. Now we consider a cycle p1 alpha 1, and with this we want to create LCM of something that equals the rest of that, p2 to pk alpha k. Let's see how we do that. So n is greater than equal this, n is p1 alpha 1 plus n minus p1 alpha 1. And if we prove n minus p1 alpha 1, then we can, if we prove n minus p1 alpha 1 greater than this, then we can use induction and say we can find some cycles that their sum is n minus p2 alpha 2 and their LCM would be p2 alpha 2 to pk alpha k by induction. So how we can prove this? It is equivalent that if I prove this, then I can prove this. Why? Because I know n is at least this. So I can say this term is at least 1 plus, if I replace here, n is at least 1 plus p1 alpha 1 to pk alpha k minus p1 alpha 1. If I prove this is because I know this one, this one is greater than the whole this one. So if I prove this greater than this, then I can prove this. So here it is equivalent that if I consider this A, this B, so it would be AB. So it is equivalent that AB minus A minus B plus 1 greater than equals 0. So A minus 1 times B minus 1 greater than equals 0, because it is obvious because A and B are greater than equal 1. Also they are greater and it's obvious. So I will use induction like here P1 alpha 1, and for n minus P1 alpha 1 I know that there are cycles L prime for example to L prime S, and I know that their sum is n minus P1 alpha 1. P1 alpha 1 plus them would be n. And also their LCM. By induction, I can say their LCM is P2 alpha 2 to Pk alpha k. And with LCM of that, P1 alpha 1, it would be this. So I proved for general n that there exist cycles with these lengths.